Okay, so our lesson today is called Not Enough Numbers. And this is our first dive or first look into statistics and number of combinations and stuff like that. So this is probably the trickiest lesson that we have in our first section. So I'm going to split this into two. We're going to look at, in total, 4 different parts. They're not going to take too long, but we'll split them up 2 and 2. So if we look at our first one, it tells us that we have to assume we have 3 standard die with numbers of 1 to 6 on each die, and we're going to use A, B, and C. So it wants to know how many total combinations that can be rolled. So if we have 3 dice, the standard dice has 6 numbers. So the way I'm going to write that is A, B, and C. So we can get 6 numbers for A, 6 numbers for B, and then 6 numbers for C as well. We would simply multiply all of those together, and we're going to get 246 different combinations that we can roll with those 3 dice. So when I'm talking about combinations, that would be if I just roll 1, 1, 1, 1, 1, 2, 1, 1, 3, so on and so forth. So we would get 216 if that were the case. So looking at our next problem right there, number 2 wants to know how many would exist if they could not all be the same number. So the way that this works is that in the first part of this question that we just did, we have the total number of combinations. There's 216. There can't be any more than that. So what we're going to do with these next few problems with 2, 3, and 4, they're going to give us restrictions. And with those restrictions, we would figure out how many cases there are or how many possibilities in those restrictions and then subtract that from the total amount, that being 216. So looking at number 2, our 3 dice cannot all be the same number. So we need to figure out first how many numbers fit this restriction that we have. So if they can't all be the same number, then they can't all be 1, they can't all be 2, 3, 4, 5, and then of course 6. So this is a total of 6 cases here where they can't be the same number. So that's 6 times where that could happen. So if that's the case, we're going to take our 216 and subtract out each of these 6 scenarios. So 210 combinations right here would be how many would work with that restriction. So we're going to look at this one more time with number 3, and I'll have you try number 4 out. So if we read number 3, it wants to know how many combinations would exist if I did not want to include when A is 2 and B is any number from 1 to 3. So this is where it can get a little tricky. So what I need to do is figure out how many restrictions that I have or how many I don't want. So I'm going to go with A, B, and C with our different numbers. So it says I don't want when A equals 2. So if I think about it, I need to think about how many numbers A cannot be. And if that's the case, it's only one number, and that's being 2. So I'm not going to write the number 2 there. Of course, there's only one number that A can't be, that being 2. So 1's going to go there. B is any number from 1 to 3. So again, I need to count and think about how many numbers that I don't want B to roll. If I think about if it's 1 to 3, that would be 3 numbers. 1, 2, and 3 fit that description. So this is where it gets a little tricky right here with C. The best way to think about this is the restriction that I have is that A cannot be 2 and B cannot be 1, 2, or 3. So let's imagine I have dice A, I roll a 2. I have dice B, I roll it, and it's also a 2. So right away that fits its restriction right there. So it doesn't matter what I roll for C, it's going to fit that description no matter what, whether that's a 1, 2, 3, 4, up to a 6. So if I meet the description of A and B or the restriction of A and B, it doesn't matter what I roll it for C. It could be any of those 6 numbers. So I have to take account for all of that. So when I go and multiply these numbers together, I'm going to get 18 restrictions right there. I could list these restrictions out. That would take some time. But once I meet these 2 that are given to me, it doesn't matter what C is. It could be any number. I'm still going to have that restriction. So I'm going to go and subtract that out. So 198 right there is going to be my final answer. So let's take a look at number 4. So it says, out of the total possible combinations, how many combinations would exist if I want to exclude when A is 5 and C is any number from 3 to 6. And then when A is 6 and C is any number from 1 to 2. So this one's a little different in the sense of now it's going to give me 2 scenarios here. So I got scenario 1 with A equaling 5 and C being any number from 3 to 6. So I don't want that. And then I have scenario 2 with A equaling 6 and C being any number from 1 to 2. So I need to take account both of these scenarios. So I need to figure out how many fit this scenario, scenario 1, how many fit this scenario, that being scenario 2, and then subtract that out. So I want you to try this one on your own, and then so pause the video and do that, and I'll have the answer and talk about it. Okay, so here is the math on that. I'll kind of quickly talk about how these numbers came to be. Scenario 1, A cannot be 5, so that's one number that A cannot be. C can't be 4 numbers, 3, 4, 5, and 6, so that's where that 4 right there comes from. If those 2 restrictions are met, B can be any number, any 6 of those, multiply that across to get a nice 24. So 24 meets scenario 1 that we don't want. Scenario 2, again, there's one number that I don't want A to be. There's 2 numbers I don't want C to be, that being 1 and 2. And then B right here is, doesn't matter what we roll, we're going to get 6 for that. So if that's the case, we multiply across, there's 12 of those that we don't want. After we do that, we're going to take each of these 2 numbers, and as you see here, I subtracted those from my total amount. So my answer is 180 combinations there. Now, if we continue with the next set of problems, we're going to look at this one, and that will conclude part 1, and then we're going to look at 2 other sets of problems in the part 2 of this video. So this time we're talking about zip codes. Let's say that every zip code has 5 digits and it's written in this form, A, B, C, D, E, where each of those letters represent a number, of course. So it wants to know what are the requirements if we use the table to the right. So just like the problem set before, the first question has to figure out the total number of combinations. So I have A, B, C, D, and E. So I just need to look over. If I look at A, it says that can be anything from 3 to 9. So if I count how many numbers that is, gotta be careful, that's actually going to be 7. So if you count 3, 4, 5, 6, 7, 8, 9, that's 7 numbers there. If I look at B, B, D, and E could be from 0 to 9. So if I count that, that's going to be 10 for each of those. And the last one is C, it could be either 2 or 3. So that's going to be 2 numbers. Multiply across, so I got 1,400 combinations that could be made here. Looking at number 6, I'll set this one up and let you try this one on your own. So realize that several ones are taken, so now we have a new set of restrictions. So it wants to know how many are available now with this set of restrictions that we're going to use. So if I look at this chart, A and B seem to be the same, but where it gets a little different right here is with C. So if C equals 2, D and E can be a select set of numbers. If C equals 3, D and E can be a select set of numbers. So this is going to be a case where I'm going to have 2 scenarios here. So I got scenario 1 and then scenario 2. So I'm going to go ahead and make my little spaces down here. And then over here for scenario 2. So my first scenario is when C equals 2 and then C equals 3. So I want you to try this out using that chart, figure out how many combinations we have for each of these scenarios, and then because we're looking for restrictions, we'll add that up and that will be our total number. So I want you to pause the video and try this on your own, and then I'll explain what our answer is going to be. Okay, so A and B are going to stay the same, so A is still 7, B is still 10. Each of these scenarios present when C equals 1 number, so each of those are going to be 1 as well. So it's really going to come down to reading our charts for D and E. So if I look at C equals 2, D can be 5 numbers, E can be 3 numbers, so that's where I get that there. And then when I look at C equals 3, I'm going to get 5 numbers there, 7 numbers there. So after I multiply those across, these are the numbers that I get for each scenario. Then I add those together and get 3,500, which is going to be my final answer for this problem. So like I said, this is I'm going to split this into 2. So if you go ahead and go over to part 2, you'll catch the rest of this lesson.